Welcome to the second video in a series of 5 on algebra basics, fractions. Let's look at multiplying fractions first. It's the easiest of the 4 things that we'll learn in this video to add, subtract, multiply, and divide. When you're multiplying fractions, such as in this problem, you can basically multiply straight across. 3 times 7 is 21, and 5 times 4 is 20. Now, I would consider this the final result of this multiplication. In some courses, you would reduce this to 1 1/20th, or in some courses you would reduce it to a decimal. This first version of the result, and by the way, all 3 of these are correct, but this first version is called an improper fraction because the numerator is higher than the denominator. The second one is called a mixed number, and of course this one is called a decimal. Now, depending on which course you're in, you'll use different formats of these numbers, but in most algebra classes, you will not use mixed numbers or decimals. You will traditionally leave everything as an improper fraction. And as a side note, that's a really bad name that they chose to give this thing because the word improper sounds like there's something wrong with it, when in fact this is the preferred answer, at least in an algebra class. Let's take a look at another problem, and let's employ the same strategy to multiply fractions that we multiply straight across. 6 times 10 is 60. 11 times 18, by the way, I worked it out on a calculator and got 198. Could have used scratch paper as well. And while 60 198ths is in some sense correct, it's not reduced. It's not expressed in the lowest terms. And in mathematics, we don't like fractions, even if they're right. We don't like them if they're not reduced all the way. So what I did is I noticed that both of these numbers were divisible by 2, so I cut them each in half. But then I realized I could reduce further because the top and the bottom are both divisible by 3, so I reduced to a factor of a third. And then it occurred to me that there are no common factors between 10 and 33 and that I can't reduce anymore. Now, while there's nothing wrong with the multiply straight across rule, there is a shortcut that's called cross-canceling, and I'd like to show you a nice shortcut here. Same problem. Suppose instead of multiplying straight across, it had caught our attention, for whatever reason, that the 6 and the 18 had a common factor. Now they're both divisible by 6. So what I can do here, as a shortcut essentially, is I can say, okay, 6 goes into 6 once, and 6 goes into 18 3 times. And then, after cross-canceling, essentially reducing in a diagonal fashion, we could then multiply straight across 1 times 10 and 11 times 3 and get the same result without having to go through as much work as I did the first time. By the way, as an afterthought, I could also have done this problem by noticing that 10 and 18 have a common factor. They're both divisible by 2. Suppose instead I had started this problem by going 2 goes into 10 5 times, and 2 goes into 18 9 times. I could have then multiplied straight across, or maybe it would have caught my eye that 6/9 is reducible. In other words, 6 and 9 are both divisible by 3. I could have then said 3 goes into 6 twice, and 3 goes into 9 3 times, and then I could have multiplied straight across. In general, it wouldn't matter. I would get the same answer regardless of method. It's worth noting that this so-called cross-canceling trick is only valid in a pure multiplication, fraction times fraction. If there's any addition or subtraction in these problems and it's no longer pure multiplication, nothing that I just said about the cancellation of common factors is valid whatsoever. Now that we've covered multiplication of fractions, I'd like to look at a special case that arises quite a bit in an algebra class. Let's look at a whole number times a fraction, such as this problem here. Some teachers will say that because the 5 is a whole number, we could express it as a fraction 5 divided by 1, which is true. After all, 5 divided by 1 is 5. And while there's nothing whatsoever wrong with that, it's not my personal style. Personally, I like to say to myself the following. If I'm multiplying a whole number times a fraction, the whole number only multiplies by the top of the fraction. So 5 times 2 is 10, leaving the 3 alone. Either way will give you the same result, but that's the perspective that I like. Now finally, I'm looking at 10/3. That's not reducible, other than to express it as a mixed number or a decimal, which is not the traditional thing to do in algebra, so I'm just going to leave it as 10/3. Here's another example. In the same strategy, the 8 is only going to multiply by the 5. 8 times 5 is 40, leaving me an answer of 40 over 2, or 40 halves. Now if you look at the two answers to these problems, one of them, you'll notice, is reducible. Specifically, the 40 halves. 40 divided by 2 is 20, and that's a better way to put your answer. Very few math teachers will accept 40 over 2 as their final simplified answer. Here's one more problem, just to show you that we have a third option. I could make the 12 as 12 over 1. I could also do the 12 times 7, as I mentioned, as my preference. There's nothing wrong with doing 12 times 7, but I thought to avoid larger numbers, in this particular case, I would use the cross-cancellation technique. In other words, looking at the 12 and the 6, noticing that they're both factors or multiples of 6, I could say the following. 6 goes into 12 twice, 6 goes into 6 once, and then multiplying straight across gives me 14 divided by 1, which, by the way, reduces to 14. Let's take a look at a division problem. Here's a fraction divided by a fraction. It should be noted that the division symbol you see in the top problem is not commonly used in algebra, and we typically, when we're doing division, we typically tend to write it as a fraction. So while these two problems you see here are the same problem, you're way more likely to see the bottom version in an algebra class. Either way, here's the rule. When you're dividing fractions, you take the first fraction and you multiply it by what's called the reciprocal of the bottom or second fraction. And you'll notice that it basically comes down to use an informal phrase, flipping over the bottom fraction. By the way, the actual definition of what two numbers being reciprocals is requires that if you multiply two numbers together and the result is 1, then those numbers were reciprocals of each other. And while that's the formal definition, students tend to think of the reciprocal of a fraction as just flipping it over. Well, what have I done here? I haven't done the problem all the way. What I have done is I've converted a division problem into a multiplication problem. I now have to do that multiplication problem. And as we saw recently in this video, multiplying fractions just requires multiplying straight across, unless cross-cancellation is needed, which in this case it was not. So the answer to this problem is 12/35. So now let's look at the more difficult operation of adding and subtracting fractions. But first, remember this multiplication problem where we discussed multiplying straight across the tops and the bottoms? If that's a rule, then shouldn't they just have made the addition rule for fractions that we add straight across the tops and add across the bottoms? 5 plus 2 is 7. 6 plus 9 is 15. Well, they could have made that a rule, but they didn't. Why did they make the rule so simple for multiplication and as we'll discover soon, not so simple for addition and it turns out subtraction. Well, ultimately, we want mathematics to represent things in the physical world, the sciences, and engineering. So all the rules that are made up in mathematics are made up in a way that will keep the whole system consistent with the scientists, so that the things that we study in real life actually correlate to the rules of mathematics. Okay, so let's take a look at this problem. I'll move it a bit here to make some space. Let's take a look at this problem. If we don't add straight across when we're adding fractions, what do we actually do? Well, it turns out we're going to look for something called a common denominator. And what I mean by that is the denominators, or the bottoms of the fraction, can be, if we can make those numbers the same, then we can add these fractions together, as it turns out. Well, the 6 and the 9 are not the same, so my goal is to find a common denominator that's consistent with both 6 and 9. What number do you think would be a common denominator that I could use to accommodate the 6 and the 9? Now I paused there on purpose because one of two things happened. Either when I paused you thought, oh, of course it's 18. Now if that popped into your mind before I showed you the 18s, then you don't really need an explanation for where I got that number. Somehow earlier in life that just became some part of your mental process and it's not a big deal. Now for other people, and you may be one of these, some of you would never have come up with 18 on your own. And if that's you, I'd like to address that issue here, how you can find the so-called common denominator before proceeding. So take your first denominator, in this case 6, and count by 6s. Notice I'm counting by 6s here. Then take your second denominator, which in this case is 9, and count by 9s. And then look at your two lists. You will eventually, if you go far enough out, have numbers in common. So any number that's on both lists is called a common multiple of 6 and 9, and we can use any of those as our common denominator. I like to use the lowest one, also known as the least common multiple or lowest common denominator, so I'm going to choose 18 and not 36. And that is the long story of where 18 came from. But of course I still have to complete the problem, so the next question is, how am I going to convert 5/6 into a fraction of 18ths? Well, 18 is 3 times as large as 6, so in some sense I have to triple this fraction, but I'm not really tripling it. What I'm going to do is I'm going to do a trick called the multiply by 1 trick. Everyone remembers from elementary school that multiplying by 1 does not change the value of a number. For example, in your mind, do 1 times your age. Guess what? You got your age because multiplying by 1 doesn't change anything, right? Now watch this cool trick. I'm going to take the 5/6 and multiply it by 1. Was that red thing that just flew in a 1? Absolutely. 3 divided by 3 is 1. In short, I'm tripling the numerator and tripling the denominator, effectively multiplying by 1, and that gives me 15/18. I'm going to do the same strategy, converting 2/9 into a fraction of 18ths. 18 is twice as big as 9, so I want to effectively double the denominator, but if I'm going to double the denominator, I have to double the numerator. Again, I'm going to multiply by 1. The thing in green that just flew in, that's a 1. 2 divided by 2 is 1, and by multiplying by 1, I'm not really changing the value of this fraction. I am doubling the numerator and doubling the denominator, which gives me 4/18. Now before I proceed, it's worth noting that I haven't changed the problem. Now you might look and say, well, you certainly have changed the problem. Well, I haven't changed the numerical values. In other words, 5/6 and 15/18 are the same number. 2/9 and 4/18 are the same number, and in that sense I have not changed the problem, I've merely changed its appearance. But look what's happened now. I have an 18 in both denominators. That's called getting a common denominator, and now I'm ready to add these fractions. So here's what you do. You add the numerators. 15 plus 4 is 19, but you keep the denominators the same. Could we have made the rule that you add the denominators as well? Well, we could have, but if we'd made that rule, our work wouldn't have played nicely with the scientists and engineers, and they probably would have rejected our rule. So the rule is, because it matches things that are consistent with the real world, we keep the denominators the same, and the numerators, we add them together. Answer, 19/18. Let's look at a subtraction problem. This time one of them happens to be a whole number. One thing I can do to subtract these is to say to myself, I need a common denominator to add or subtract fractions. Well, the 4 does not appear to have a denominator, so I'm going to use the fact that 4 divided by 1 is 4 to give it a denominator. But my denominators don't match, so I could do the multiply by 1 trick again. This thing that just flew in red, that's a 1. If I multiply by 1, I will change 4 over 1 into 20 over 5. And notice I've achieved my common denominator. And now subtraction, just like addition, requires us to keep the denominator the same, so all I've done here is 20 minus 2 is 18, but I've left the 5 alone. The answer to this problem, 18/5. Now while I am done with this problem, I would like to mention an alternate way you could have done this. Now, this won't work for everybody. See if this works for you. Some people are able to do these problems in their head. Here's my thought bubble. Now see if this is you. If in elementary school you were taught to do 4 minus 2/5 and immediately know that that would leave 3 3/5, this is a great shortcut for you. If you have no idea where that came from, please ignore me at this point. But if you know that, then you can just convert 3 3/5 into an improper fraction by doing 5 times 3 plus 3, and it would give you the same result, allowing you to do this problem in your head. Again, that method is definitely not for everybody, but if it is something that you think you can handle, just remember, you don't always have to do math the exact formal way that a teacher tells you if you have better methods that work for you. Well, now that we've learned how to add, subtract, multiply, and divide fractions, that completes the second of 5 lessons on algebra basics.